Among all the questions humans have dared to ask, few are as unsettling, or as profound, as the idea that the universe itself might be a simulation. Popular imagination often turns this concept into science fiction. Computer screens, digital grids, futuristic beings typing code. But in real physics, the word simulation has a very different meaning. It is not about machines or creators. It is about whether the fabric of reality is, at its deepest level, an informational structure, a system whose laws arise from the way information is stored, transformed, and preserved. Modern physics already hints at this possibility. Quantum theory tells us that particles do not have definite properties until information about them is extracted. Black hole physics suggests that information is never destroyed. Cosmology implies that the universe has a finite capacity to store information. These discoveries force us to confront a radical idea. Perhaps information is not a description of reality. Perhaps it is the foundation of reality. And so we are led to a poetic question. If reality is a kind of code, then what processes are executing that code? This is not a metaphor. It is a serious philosophical and scientific inquiry that intersects with cosmology, quantum mechanics, and the study of the limits of physical law. In this video, we will examine the real scientific arguments, not the myths. We will explore Nick Bostrom's logical trilemma, the possibility that space and time are fundamentally discrete, the hints of pixelation at the Planck scale, the idea that quantum randomness may be the universe's generator of unpredictability, and the clues hidden in entropy, holography, and the information content of space-time. This is not about sci-fi fantasies. This is about understanding whether the universe behaves like a continuous physical reality, or like an informational structure woven from bits, quanta, and mathematical rules. A question that once belonged to philosophy is now moving toward physics. And in exploring it, we may learn more about the nature of reality than any previous generation could imagine. The idea that the universe may be built from information is not a metaphor born from computers or modern digital culture. It is a concept rooted in the work of physicists who tried to understand what the world is made of at the most fundamental level. Among them, the visionary John Archibald Wheeler proposed a striking phrase, "it from bit." By this he meant that every physical entity, every particle, every field, every event, may ultimately arise from binary choices, from fundamental units of information. Reality, in Wheeler's view, is not made of matter first, but of answers to yes or no questions embedded in the fabric of the universe. This perspective aligns naturally with quantum mechanics. A quantum state is not a solid object but a carrier of information about possible outcomes. Before measurement, a particle does not have a definite position or momentum. Instead, it encodes probabilities, information about what might happen if we observe it. The act of measurement forces the quantum system to reveal one outcome, collapsing the cloud of possibilities into a single piece of information. In this sense, the quantum world behaves less like a mechanical machine and more like an information processor. If quantum theory suggests that information is fundamental, thermodynamics and computation give this idea physical weight. Rolf Landauer famously stated, "Information is physical." Erasing a bit of information requires energy. Recording and transforming information has thermodynamic consequences. And Jacob Bekenstein discovered that there is a maximum amount of information that can be stored in a given region of space, a profound limit that ties together entropy, gravity, and quantum mechanics. Information is not an abstract quantity floating above matter. It is woven into the structure of space-time itself. This becomes even more striking when we consider black holes. According to Stephen Hawking and Leonard Susskind, black holes do not destroy information, even though nothing can escape their gravity. Instead, information about everything that falls into a black hole appears to be encoded on its event horizon, the two-dimensional surface surrounding it. This leads to the holographic principle, the idea that all the information needed to describe a volume of space can be stored on its boundary. Reality, in this view, is like a hologram. The three-dimensional world we experience may be a projection of deeper information written on a distant surface. This principle does not claim that the universe is a simulation. Instead, it shows that information is a fundamental building block of physical law, that the geometry of space, the behavior of particles, and the evolution of cosmic structures may arise from underlying informational constraints. If Wheeler is right, and it truly comes from bit, then reality is not a solid stage but a dynamic informational network. Particles are excitations of fields, fields are repositories of information, and the universe itself may be the unfolding of an informational process so vast and intricate that it resembles what we might call a cosmic computation. In exploring this idea, we are not stepping away from physics. We are stepping deeper into its foundations. One of the boldest ideas in modern theoretical physics is that space and time may not be continuous. Instead of forming a perfectly smooth, unbroken fabric, reality itself might be made of tiny, indivisible units, the pixels of the universe. This concept arises naturally from the fundamental scales of nature, the most famous of which is the Planck length, approximately 1.6 times 10 cubed meters. It is so small that comparing it to the size of a proton is like comparing a proton to a galaxy. At this scale, our familiar notions of distance and geometry begin to lose meaning. Accompanying this is the Planck time, about 5.4 times 10 seconds, the smallest possible unit of time before our equations break down. In classical physics, time flows smoothly, but at the Planck scale, the very idea of flow becomes questionable. Below these scales, space and time may not exist in the way we understand them. They may instead emerge from something more fundamental, a discrete, quantum structure. What does it mean for reality to be discrete? It means there may be no such thing as an infinitely small distance, no infinitely smooth surface, no perfect continuum. Instead, space may be grainy, built from finite units of geometry, just as matter is built from atoms and fields from quanta. This idea is central to several leading theories of quantum gravity. In loop quantum gravity, space is described as a network of finite loops, forming a structure known as a spin network. These loops evolve over time into a web of relationships called a spin foam. Space is not something that exists. It is something that is constructed from these discrete nodes and links, each carrying a quantized amount of area or volume. Geometry itself becomes an emergent property. Another approach, known as causal set theory, suggests that the universe is made of discrete events connected by cause and effect relationships. Space-time is not continuous but resembles a growing graph of fundamental atoms of existence, each linked to others in a strict causal order. From this network, the illusion of smooth space-time appears at large scales, much like a fluid appears smooth even though it is made of molecules. If space-time is indeed pixelated, can we detect it? This is one of the great experimental challenges of the 21st century. Researchers search for signs of discreteness in high-energy cosmic rays, gravitational wave signals, and interferometer experiments like the Femilab halometer, which attempted to detect subtle jitter in space-time itself. Although no definitive evidence has been found, the search continues, pushing the limits of our instruments and imagination. If future experiments reveal that space and time have a smallest building block, it would mark a revolution comparable to the discovery of atoms or the quantum nature of light. It would mean that the universe is not a smooth canvas but a finely woven tapestry, one whose pixels lie hidden beneath the threshold of all current observation. In asking whether reality is digital or continuous, we are not merely speculating. We are probing the very architecture of existence. In 2003, philosopher Nick Bostrom proposed an argument that shook both philosophy and physics, not because it claimed we are living in a simulation, but because it suggested that, under reasonable assumptions, one of three statements must be true, and each is unsettling in its own way. His argument is mathematical, not metaphysical, based on probability, not speculation. Bostrom begins by imagining a future civilization capable of building computers far beyond anything we can conceive. If technological progress continues, such a civilization could reach a point where their computational power is so immense that they could simulate entire planets, ecosystems, or even conscious beings. The argument then unfolds. 1. Advanced civilizations never reach that level of computational power. Perhaps technological civilizations inevitably self-destruct, through war, resource collapse, or other existential threats, before they can build planet-scale simulations. If this is true, the universe might be full of life that never survives long enough to explore its full potential. 2. Advanced civilizations exist, but they choose not to run simulations. Maybe they consider simulations unethical, dangerous, or simply unnecessary. Perhaps they are indifferent to recreating their past. If so, the universe might be full of hyper-advanced societies, but none of them look back. None of them press run. 3. If civilizations survive and if they run simulations, then simulated beings vastly outnumber biological ones. Therefore we are almost certainly simulated. This is the most provocative conclusion. If even a tiny fraction of advanced civilizations create billions of simulated conscious worlds, then statistically, it is far more likely that we are in one of these simulations than in a base-level universe. The argument does not rely on physics or philosophy, it relies purely on numbers. But Bostrom's argument has weak points and deep challenges. One major issue is the problem of consciousness. Would simulated beings truly be conscious, or merely imitate consciousness? If consciousness arises from physical processes alone, perhaps it can be simulated. But if it depends on something irreducible, qualia, or non-computable elements, the argument collapses. A second issue is the infinite regress problem. If simulated beings create simulations of their own, and those simulations create further simulations, then the number of simulated universes becomes infinite. Probability theory breaks down. Which level is real? Is there even such a thing as a base reality? A third concern involves ethics and physics. Would an advanced civilization choose to simulate worlds filled with suffering, randomness, or entropy? Would they simulate the entire universe, or only small patches relevant to observers? If simulations cut corners, approximating distant galaxies or unobserved regions, they might leave detectable glitches or limits in physical laws. But so far, physics shows no clear signs of such shortcuts. Most importantly, Bostrom's argument does not say we are definitely simulated. It says that unless one can reject the first two propositions, the third becomes statistically dominant. It is a philosophical thought experiment phrased in the language of probability, a way to probe the assumptions we make about consciousness, technology, and the structure of reality. In the end, Bostrom does not claim the universe is a simulation. He claims that our answer to this question reveals what we believe about the future of intelligent life, the nature of consciousness, and the limits of technology. His argument serves less as a conclusion and more as a mirror, reflecting our deepest uncertainties about reality itself. While philosophers frame the simulation question in terms of probability and logic, physicists approach it from a different angle: the fundamental structure of space, time, and information. Three major scientific perspectives, from Gerard T. Hooft, Silas Bean's team, and Leonard Susskind, offer insights that, while not explicitly claiming the universe as a simulation, show that reality behaves as if it may be informational at its core. Gerard T. Hooft, Nobel laureate, is one of the earliest proponents of the idea that the universe might be holographic. In his formulation, the information content of any region of space does not scale with its volume but with its surface area. In other words, a three-dimensional region may be fully described by data encoded on a two-dimensional boundary. This is the foundation of the holographic principle, the possibility that the 3D world we experience is, in some sense, a projection of information stored on a distant cosmological surface. T. Hooft did not mean this metaphorically. He meant that the mathematics of quantum gravity demands it. If this is true, the universe itself is structured like a massive informational system. Leonard Susskind expanded this idea dramatically through the black hole information paradox. For decades, physicists believed that black holes destroyed information, swallowing it forever. But Susskind showed that such destruction would violate quantum mechanics. Instead, he proposed that the information about everything falling into a black hole is encoded on the black hole's event horizon, another holographic surface. This insight unified gravity, quantum theory, and thermodynamics, suggesting that information is the true currency of physical law. If black holes preserve information by encoding it on surfaces, then perhaps the entire universe operates the same way. The third perspective comes from an unexpected direction: lattice simulation physics. Silas Bean and collaborators proposed that if the universe were represented on a discrete spatial grid, like a lattice in a computer simulation, then certain simulation artifacts should appear in the behavior of extremely high-energy cosmic rays. On a lattice, particles cannot have arbitrarily high momenta. They experience angular distortions and preferred directions, just as graphics in a video game reveal the resolution of their underlying grid. Bean suggested that cosmic rays might show similar anisotropies, slight directional biases reflecting the pixelation of space-time. If such signatures were ever detected, they would not prove simulation, but they would show that space has an underlying discrete, computational geometry. These arguments do not claim a programmer or a computer. They ask a deeper question: is the geometry of the universe a consequence of computation-like rules? Is gravity the emergent behavior of information flow? Are quantum fields discrete systems that update according to fundamental computational processes? Some frameworks of quantum gravity already point in this direction. If space-time emerges from entanglement patterns, if geometry forms from networks of quantum bits, or if gravity arises from information flow across holographic surfaces, then the universe behaves less like a continuous container and more like a self-executing informational system, a structure in which physics is the operation and reality is the output. None of these ideas claim that we are in a simulation run by external beings, but they collectively suggest that information, not matter, not energy, not space, may be the most fundamental ingredient of the universe. In this sense, the universe may not be a simulation, but it may operate as if it is one. At the heart of quantum physics lies a phenomenon so unsettling, so unlike anything in classical science, that it reshaped our understanding of reality: quantum randomness. In the quantum world, events do not unfold according to hidden mechanisms or deterministic rules. Instead, particles behave as if the future is fundamentally undecided until the moment of measurement. An electron's position, a photon's polarization, a neutrino's flavor, all remain suspended in a haze of probability until an observation collapses that cloud into a single outcome. This randomness appears to have no classical explanation. It is not like the randomness of a coin flip, which is deterministic but unpredictable due to complexity, nor is it the randomness of thermal noise or chaotic systems. Quantum randomness is intrinsic. The equations of quantum mechanics give only probabilities, never certainties. Nature seems to roll its own dice. This raises a profound question. Is quantum noise simply the universe's built-in generator of randomness, or could it be a signature of something deeper? If the universe were a simulation, not in a sci-fi sense, but in the informational sense, then even a perfect simulation would require randomness. No computation can produce true unpredictability unless it draws from a source of entropy. The quantum vacuum, with its constant flickering of virtual particles and spontaneous fluctuations, could be interpreted as an entropy engine, seeding the universe with unpredictability. This interpretation does not prove simulation, but it intriguingly parallels the way random number generators operate in computational systems. Yet quantum fluctuations are not pure chaos. They exhibit subtle correlations that follow exact mathematical rules. Entangled particles maintain perfect correlations across space, even when separated by light years. The structure of noise in the cosmic microwave background, the distribution of electron energy levels, the timing statistics of radioactive decay, all follow precise quantum distributions that no classical random generator could imitate exactly. This leads to another deep question. Could we distinguish true quantum randomness from simulated randomness? In principle, yes, but only if the simulation used imperfect random algorithms. A computer-generated random number sequence eventually repeats or reveals patterns. Quantum randomness, by contrast, has no known mechanism and displays no periodicity. Experiments using quantum random number generators have shown that quantum processes outperform all classical algorithms in unpredictability. However, if the hypothetical simulation used quantum-level randomness itself, then detecting a difference becomes nearly impossible. The simulation would be indistinguishable from reality because it would use the same fundamental principles. Thus, quantum randomness sits at the crossroads of physics and philosophy. It may be a window into the deepest workings of reality, or simply the universe performing its most fundamental computation. It may reflect pure indeterminacy, or it may be part of a larger informational architecture whose purpose we do not yet understand. What we do know is this: quantum fluctuations are not noise in the sense of error. They are the raw texture of reality, the microscopic tremors from which stars, galaxies, and life itself eventually emerged. Whether this randomness is absolute or engineered, fundamental or emergent, remains one of the most important and mysterious questions in modern science. One of the most fascinating bridges between physics and the simulation hypothesis lies in the study of entropy and information limits, the rules governing how much information can exist within any region of space. These are not philosophical questions. They are physical laws, encoded directly into the mathematics of black holes, quantum theory, and thermodynamics. The first major insight came from the Bekenstein bound, which states that any finite region of space can store only a finite amount of information. This maximum is not determined by the volume of the region, but by the surface area of its boundary. In other words, the information contained inside a sphere is limited not by how big the sphere is, but by how large its surface is. This is a deeply counterintuitive result, unless one assumes that reality behaves like an informational system, where the memory capacity of a region scales with its boundary, not its interior. Nowhere is this more dramatic than in black holes. Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy, the measure of how much information it contains, is proportional to the area of its event horizon, not its volume. Leonard Susskind later argued that this implies a radical truth. Black holes behave not like physical objects swallowing matter, but like logical structures processing information. The event horizon acts as a storage surface, encoding details about everything that falls in. This principle ultimately led to the holographic idea. A region of space can be fully described by information stored on its boundary. Such constraints look suspiciously like the rules of an informational system. A computer simulation, too, has finite storage. It cannot encode infinite detail in a finite region, because information would diverge. Yet the universe obeys similar limitations, suggesting that, at its core, reality might follow rules that resemble the architecture of a computational system. Entropy also plays a role in the arrow of time, the fact that time flows in one direction. But why does it? In fundamental equations of physics, time is symmetric, nothing prevents events from happening backward. And yet the universe clearly evolves from order toward disorder, from low entropy toward high entropy. Why? One interpretation is simply the second law of thermodynamics. Another interpretation is that the growth of entropy resembles a system executing a process, like computation unfolding step by step. Computations move irreversibly forward because each step builds upon the last, and reversing the entire system would require erasing information, an enormously costly act, tied again to Landauer's principle. This raises a provocative question. Is the arrow of time not merely a physical phenomenon, but a sign of the universe updating itself according to informational rules? If the universe behaves like a computation, then entropy is not chaos, it is bookkeeping. It measures how much of the system's information has become irreversibly distributed, how many pathways the universe can still take, how much state space remains unexplored. The fact that entropy always increases could reflect an underlying algorithm that never rewinds, only progresses. None of this proves that the world is a simulation, but it shows that the universe behaves as if information is fundamental, as if entropy is an unavoidable consequence of how information flows, and as if the laws governing reality mirror the constraints of any system that processes and stores information. The more we study entropy, the more we see not disorder, but the quiet logic of a universe that may be structured like code. If the universe truly has an underlying informational or discrete structure, then in principle, there should be ways to detect it. But searching for such signatures is extraordinarily difficult. If reality is emergent from deeper rules, those rules would likely operate at scales far smaller and energies far greater than anything humans have ever directly observed. Still, physicists have proposed experimental strategies that might reveal clues, not by proving simulation, but by exposing deviations from perfect continuity in space-time. One idea is the crystallization of space at extremely small scales. Just as matter at low temperatures forms lattices or grids, some theories of quantum gravity suggest that space itself may behave like a discrete structure at the Planck scale. If this is true, then the universe is not infinitely smooth. It is granular, composed of minuscule cells whose size defines the smallest meaningful distance. Such discreteness would subtly influence the motion of high-energy particles. At the highest cosmic energies, their trajectories might show preferred directions or slight asymmetries, the way light in a simulated world sometimes reveals the pixels beneath its surface. Another experimental approach focuses on the possibility of holographic noise, tiny fluctuations in distance that arise not from matter, but from the limited information capacity of space itself. If space-time is a holographic projection of deeper information, then any measurement of position or distance might contain a faint, irreducible jitter. The Femilab holometer was designed to search for exactly this effect. It used two exceptionally sensitive interferometers placed side by side, looking for correlated noise patterns that would indicate that spacetime itself is fluctuating at its foundational layer. The goal was to detect vibrations of reality, a trembling of the quantum geometry beneath our world. Although the results were consistent with standard physics, the experiment demonstrated that we can, at least in principle, probe the informational fabric of the universe. A third avenue involves cosmic rays, particles that travel across billions of light-years with energies far beyond those created in laboratories. If the universe were built on a discrete spatial lattice, then particles with energies near the lattice's resolution limit might behave differently. Their momenta could be constrained, their arrival directions might show grid-like patterns, their energy distribution could reveal the resolution scale of space itself. This idea arises from computational physics. In any simulation, extreme values reveal the limits of the underlying numerical grid. The universe, if discretized, might reveal similar boundaries. But despite these imaginative approaches, no experiment has yet found definitive evidence of discretized space, holographic jitter, or lattice constraints. Every anomaly so far has yielded to conventional explanations or experimental noise. This does not mean the simulation hypothesis is false. It simply remains beyond the reach of our current instruments. If the universe is discrete, the pixels are far smaller than anything we can resolve. If it is holographic, the surface encoding reality is too distant or subtle to detect. And if it is a simulation, its architecture may be more elegant than any artifact we can hope to uncover. Experimental physics thrives on limits, on pushing against what we can measure. For now, the structure of reality remains smooth to our finest tools, quiet to our most sensitive ears, and seamless to our deepest mathematical probes. If there is a boundary, a grid, a code beneath the universe, it hides in scales we have not yet learned to reach. For all its elegance and philosophical appeal, the simulation hypothesis faces serious counterarguments, challenges that cut to the core of physics, logic, and metaphysics. These criticisms do not simply dismiss the idea. They expose the deep assumptions underlying it and remind us that interpreting the universe as a simulation is far from straightforward. One fundamental critique is that the simulation hypothesis does not actually answer anything. It simply relocates the mystery. If our universe is a simulation, then what is the nature of the world that runs it? Who or what created that world? And if that world is simulated, what runs the one above it? This leads to an infinite regress, a chain of universes nested within universes, with no ultimate foundation. Instead of simplifying the nature of reality, the hypothesis can multiply realities without resolving the question of why anything exists at all. Another objection challenges the notion that mathematics is synonymous with code. The universe follows mathematical laws, but mathematical law is not the same as computational instruction. The equations of physics do not imply a programmer in the same way that the geometry of a circle does not imply a draftsman. When we describe reality using mathematics, we are describing patterns, not necessarily programs. The fact that physics resembles computation may simply reveal the deep unity of natural law, not a digital architecture. A third critique questions the feasibility of the simulator itself. To simulate an entire universe with perfect fidelity, including quantum fluctuations, gravitational dynamics, chemical reactions, and conscious beings, a simulator would require unimaginable energy and computing power. Yet physics imposes limits, even on hypothetical civilizations, entropy constraints, information bounds, and the energy requirements of computation. It is far from clear that a simulator could operate outside these constraints. Simulating a universe as large and detailed as ours might demand resources equivalent to the universe itself. Finally, there is a philosophical counterargument. Perhaps physics is fundamentally real rather than emergent from computation. The simulation hypothesis implicitly assumes that computation is more fundamental than physical law, that reality is built from information processing. But this reverses centuries of philosophical reasoning. It is just as plausible, and perhaps more economical, to suppose that the universe exists as a physical system governed by its own intrinsic laws, without needing to be executed on a deeper substrate. The simulation hypothesis may reflect our computational worldview, rather than the actual structure of the cosmos. These counterarguments do not prove the simulation hypothesis wrong, but they reveal that it rests on assumptions that are far from settled, assumptions about consciousness, ontology, information, and the nature of physical law itself. Whether or not we live in a simulation, the question forces us to confront the limits of our understanding and the deep philosophical foundations beneath science. Sometimes the hardest thing to accept is not that the universe could be simulated, but that it may simply be. In the end, the simulation hypothesis leaves us in a place that is both humbling and strangely beautiful. After exploring the arguments, the physics, the philosophy, and the limits of what we can observe, the honest conclusion is simple. There is no evidence that we live inside a simulation, and no evidence that we do not. The question remains open not because it is mystical, but because it touches the deepest foundations of what we call reality. What this journey truly reveals is not an answer, but a perspective. It reminds us that physical reality is far more subtle, far more layered, and far more astonishing than our daily intuitions allow. Whether the universe is built from continuous fields, discrete bits, or something even more fundamental, it behaves with a precision and coherence that defy any simplistic explanation. Our equations work. Our experiments speak. And yet beneath the stability of the physical world, we repeatedly encounter limits, Planck scales, information bounds, quantum uncertainties, that hint at something deeper than our senses can grasp. Perhaps, then, the real lesson is not that we should search for a programmer or a machine behind the stars, but that we should refine our understanding of what reality means. The notion of simulation may be less about computer code and more about structure, the mathematical backbone upon which the universe is built. Maybe consciousness, matter, and space-time emerge from principles we have only begun to uncover. And so we end with a thought that merges science and poetry. Perhaps we are not inside a simulation. Perhaps we are inside an equation. And while we struggle to solve it, the universe continues to run its code. Whether written in bits, quanta, or curvature, the laws of the cosmos unfold with perfect consistency. And as long as they do, our role is not to fear the question, but to keep exploring the pattern.